Howdy, this is Mr. Potter. In today's video, we're going to be talking about recursion. The idea behind recursion is that we're going to have a function, a method, essentially call itself in order to complete a task. The idea is that whenever there's something where I can do a repeated option a certain number of times, a process that can be repeated a certain number of times to solve a problem, where I eventually get closer and closer to something called a base case, some base situation which always has the same result. I can use the technique of recursion in order to solve that. So I'm going to go ahead and just real quick create a class here. So we'll do public class recursion 1. And what I'm going to do here is I'm actually going to create some methods here. And the idea is that I'm going to use these methods to perform some tasks. The usual method that's used when we're talking about recursion is the idea of a Fibonacci sequence. So a Fibonacci, Fibonacci sequence starts off with two numbers, and then every successive number is the sum of the previous two numbers. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, and so forth. And so these numbers do get very large very quickly, but the idea here is that each number is the sum of the previous two numbers. In other words, the Fibonacci number for n is equal to the Fibonacci number for n minus 1 plus the Fibonacci number for n minus 2. And our base case is that if n equals 0 or n equals 1, then f of n, my Fibonacci number, equals 1. So the idea here is that I do eventually reach a base case. The base case is I'm adding successive numbers, but if I ever have to evaluate f of 0 or f of 1, I'm going to get a 1 out of it. So we're going to talk about how to write this method. So I'm going to go ahead and write public static int fib, and I'm going to have int num as a parameter. And one of the first things I want to do is I want to deal with the base case. So the idea here is that I'm supposed to be returning an integer. So if num is equal to 0 or num is equal to 1, then I want to deal with my base case and just return a 1. Else, and of course remember, because I'm returning, I don't actually physically have to type the else, but I like to put the comment here to kind of remind myself that this is the secondary case to a conditional statement. What I want to do is I want to return fib for n minus 1 plus fib for n minus 2. And so what's going to happen is to calculate a number like fib 4. What's going to happen? It's going to have to say fib 4 is equal to fib of 3 plus fib of 2. But then we're going to have to calculate what is fib of 3. Fib of 3 is really fib of 2 plus fib of 1. And fib of 2 is really equal to fib of 1 plus fib of 0. But what's going to continue to happen here is I need to evaluate fib of 1 now. Now I know that this is fib of 1 plus fib of 0. And that takes care of the fib 2 part, plus fib of 1, which is 1, plus this other fib of 1, which is 1, plus this other fib of 0, which is 1. And so what I've got here is I've really got 1 plus 1 plus 1 plus 1 plus 1, which is equal to 5. And if I take a look at my sequence that I had up here, this is 0, 1, 2, 3, 4. I find my fourth Fibonacci number is 5. So this is the process of how we're doing this Fibonacci number, and I think this really does illustrate the idea of how we eventually reach a base case. So in my main, public static void main string args, so what I'm going to do is I'm just going to do system.out.println fib of 5, which should be 8 according to the list I've got at the top. System.out.println fib of 10, which is going to be a little bit larger number, and system.out.println fib of 0, just to make sure that my base case works. So I'm going to go ahead and compile this. Hopefully I don't have any stupid errors. Just a couple. So the idea here is that I cannot find symbol, so it's not n minus 1, it's num minus 1. Lovely. Num minus 2. So now if I compile this and try and run it. So I've got this list of Fibonacci numbers up here. It says Fibonacci sub 5 is there's my 0, 1, 2, 3, 4. There's my 5th Fibonacci number. The 6th number is 13. The 7th number is 21. The 8th number is 34. The 9th number is 21 plus 34, which is 55. And if I take 34 plus 55, I get 89, which is what I'm saying the 10th Fibonacci number is. And then, of course, I've got my base case, Fib 0 is 1, because that's taken care of with my if statement. So the main idea here is that I'm going to be reusing code. Notice that to find the Fibonacci of a particular value, I had to find the Fibonacci number of the two preceding values. And really, I'd like to take care of this real quick and just kind of say if num is less than or equal to 1, because that way I'm kind of protecting myself. If they ever give me a negative number, I'm not going to run out of memory, because that is something that you do have to watch out for when you've got a recursive method, especially one that really forks like this. Notice that every time I do a calculation, it kind of splits up. In order to calculate the Fibonacci of 4, I actually had to figure out Fib 3, Fib 2, Fib 2, Fib 1, Fib 1, Fib 0, Fib 1, Fib 0. I actually had to figure out 8 Fibonacci numbers, which, by the way, is not a coincidence. The fact that in order to determine the 5th Fibonacci number, I had to do the 6th Fibonacci number of calculations. There actually is a mathematical proof behind that. What that means is that if I was to tweak this to, say, 20, these numbers grow so rapidly that I'll actually see a physical slowdown in how long it takes to calculate this. So I get 10,946. If I pump this up to 30, then it's going to be a little bit more slower. And I can actually run into a situation where the process, notice the gap there, notice how long it took to actually calculate Fibonacci of 40. And if I up that up to 50, then I'm going to see a long pause here. And if that number is too big, I will actually run out of memory in Java. because it's going to have so many different forked processes, so many different function calls, because fib of 50 requires two calls, 49 and 48. And then each of those require two more calls. And each of those require two more calls. So I actually end up with this triangle that spirals down. And notice it still hasn't given me the calculation. I doubt it would give me the calculation by the time this video ended. So I'm going to go ahead and pause that and just make it a safe number like 30, which worked with no problem. So I do have to be careful with this situation. The thing is, the code here is very elegant. Notice that basically we've got it down to just 3 lines of code. If something is true, return, and then another return statement. The code is very concise, but I do run the risk of, because each one of these function calls ends up forking two other function calls out, splitting out like the tines of a fork, I run the risk of running out of memory. And this is kind of the continuation of a trade-off that we've discussed a couple of times, where I can do something with just a little bit of code that takes a lot of memory, or I can do something that takes a lot of memory but a little bit of time, or something that takes a little bit of memory but a lot of time. And there are trade-offs whenever you're having to write a program. Just something we need to be aware of. So this is my first recurring method. So I've basically got a Fibonacci method. The next method, and we've actually talked about this before, public static int, let's go ahead and call this PAL, int base, int exponent. And so the idea here behind this method is that to raise a number to a power, what I'm going to do is, if I wanted to have something like 5 to the 4th, I know that it's supposed to be 5 times 5 times 5 times 5. But it's convenient for me to think of 5 to the 4th as being equal to 5 times 5 to the 3rd. In other words, what we're doing is, for each power, multiply the base by 1 less power of that base. So in other words, I've got here 5 to the 4th, which is really 5 times 5 cubed. And then I can say, well, now if I want to find 5 cubed, that's really 5 times 5 squared. And if I want to find 5 squared, that's really 5 times 5 to the 1st. So I need to know my base case. And the base case is that if I have any positive integer that's raised to the 0 power, as long as it's a positive integer raised to the 0 power, I'm going to get a 1. And even if I had a negative base that's raised to the 0 power, I end up with 1. There's just some special case whenever I'm dealing with the base of 0. Quirky things happen. We really can't determine what that value is. So I'm going to go ahead and type the code for PAL. And so the first thing I'm going to do is I'm going to deal with the base case. And the base case is basically going to say if my exponent is equal to 0, then I want to return 1, because anything to the 0 power is 1. And then, of course, I don't have to type else, but I do have a second part of this conditional statement. What I'm going to want to turn is I'm going to want to return my base times the result of PAL for base and exp minus 1. Now, I don't have to worry about a situation where I've got a fractional exponent where subtracting 1's never going to hit 0, because I've kind of protected it with int. The only thing that I'm going to have to worry about is if this is a negative number. So I'm going to actually want to deal with that beforehand. And I'm going to say basically deal with erroneous data. And so what I'm going to do is I'm going to say if base is equal to 0 or actually let's just say if the exponent is less than 0, then we'll go ahead and return negative 1, which we're going to call an error case. And that's why I'm saying that I could basically just say, essentially I can make this a precondition. Assume base and exponent are both greater than or equal to 0. Actually, I probably need to assume that base is greater than or equal to 1, and exponent is greater than or equal to 0. So I can put that as this erroneous data that I'm dealing with. So if the exponent is less than 0, or my base is less than or equal to 0, then we'll return, this is our error case. And then, of course, I've got an else that deals with this base case. and then this. So I'm going to go ahead and tweak my main. I'm going to comment these out because I don't really need to see this. But what I can do is I can system dot out dot print line pow 5 comma 4, and I'll do system out dot print line. If I could spell system correctly, that'd be wonderful. System dot print line pow let's do 2 comma 12, and system dot out dot print line pow. I will go ahead and check this out. So let's say I want to raise 1 to the negative 4th power. So what should happen is my third case would actually be a bad situation. Notice it comes out to a bad situation. 5 times 5 is 25. 25 times 5 is 125, and 125 times 5 gives me the 625. If I take 2 to the 12th power, I end up with 4,096. And if I try and raise something to a negative exponent, I trigger my error condition. So again, fairly elegant code. I could use a loop here instead, and that would work fine as well. I could have also used a loop up here, basically saying 1 plus 1, and then just basically keep track of what the previous 2 Fibonacci numbers were in temporary variables. But the idea here is to show you how I can have recurring code, repeating code, code that calls upon itself, codes that eventually reach a base case. So I want to do one more example of a recursion function, and that's the idea of a linear search. The whole idea by a linear search is that I want to search for an item in a list starting in the 0th position, and if it's not in the 0th position and I still have more boxes to search, then search in the next position, and if it's not there, search in the next position. And I want to return the index if I find it, and I want to return -1 if I don't. So what I really have here is I really have 2 base cases. Case 1, I find the element, I return the index. And base case 2 is I reach the end of the list, and I return -1. Otherwise, what's going to happen is the result of my linear search is going to be a linear search on the rest of the list. So we're going to go ahead and write this out. So public static int linear search, and I'm going to have some int array called array, and I'm going to have a int called the target. And what I want to do is I want to deal with the base case. So remember, I have two base cases. The first thing that I'm going to do is I actually need to have a third parameter in here for int current search, current index. So what I'm going to do is if array sub current index is equal to target, then return current index. In other words, we found it. And if current index is equal to array dot length minus 1, basically if I add 1 to the current index, I'm going to find myself falling off of the list, then return -1. We didn't find it. Didn't find it. And of course, there's a hidden else here that we didn't write. There's a hidden else here that we're not going to write. And this is our iteration, the idea that we're supposed to be getting closer and closer to the base case. So what I want to do is I want to return the result of linear search for int array, so for array, my target, and I want to start searching at the next spot in the list. Now, of course, no user is going to call on such a method by saying, "Oh, I think it's in box 3." They're just going to say, "Find what I'm looking for." So we're actually going to overload this method. So public static int linear search with an int array called array and an int target. And what we're going to do is we're just going to return the result of linear search with my array, with my target, and with 0. So in other words, if the user just wants to find an element in the array and doesn't give us an initial place to search, we're going to start searching at 0. And if it's in 0, that's great. We're going to return that index. If it's not at 0, if we actually have run off the end of the list, then we're going to return -1. But if it's not at 0, then we want to search at current index plus 1. I want to search at the next spot in my list. So after I search in spot 1, if I haven't found it, search in spot 2. If I haven't found it, search in spot 3. So I'm not going to write code to apply this because it's pretty straightforward what's happening here. If it's not in box 7, then I look in box 8 and I return the results of what happened if I looked in box 8. It's basically me asking my son if he's found something, and if he has it, he'll give it to me. If he doesn't have it, then he's going to ask his best friend, and if his best friend has it, his best friend will give it to his son, who will give it to me. Otherwise, his best friend will ask their good friend, and it's going to be a chain going on until I've exhausted the list, gone through everyone that everyone knows, or I found the element. So I'm either going to find the element because it's somewhere, or I'm not going to find the element because no one knows where it is. So here's a couple of examples, a few examples of how to use recursion. What's really important is this idea of a base case, the idea that I need to eventually get to a stopping point, because we could go on forever. And we've seen the trouble that's arisen when we have infinite loops. The idea is that we really need a base case, and we really need a situation that gets closer to the base case. So in the case of linear search, the idea that we're adding 1 each time, that gets us closer to our base case. In our power, the idea that I'm subtracting 1 from the exponent, that's getting us closer to our base case where our exponent is equal to 0. And our Fibonacci, the fact that we are checking the Fibonacci for the 2 succeeding values of num, gets us closer to our base case where we return just a 1. So that's our first delving into recursive methods. We're going to talk next time about how to deal with recursion with more complex data structures. We've already seen it with arrays, but we can even do recursions with matrices, but that's for another day. Once again, this is Mr. Potter. Thank you for watching. Have a great day.